We are going to move right along into periodic trends. So that wraps up electronic configurations. I knew we could get through that quickly. And now we got periodic trends to talk about. There are three periodic trends. So let's stop and just even talk about what does periodic trends mean? Well, this is a trend on the periodic table. So like what happens is there a trend as we go across a period from left to right? What's happening to the size of the atoms? Is there a trend as we go down a family, a group, a column? What's happening to the size of the atoms? Well, there are three things that have a pretty, I guess you would say, linear trend. These are not laws. There are hiccups. There are blips in the trend, which we will talk about, and we can explain some of them. But these are statements that, like, in general, as you go across a row, the atoms get, in fact, smaller. As you go down a column, the atoms get bigger, right? So the first one we're going to talk about is atomic size. And then the next periodic trend we're going to talk about is ionization energy, which is going to be the amount of energy needed to remove an electron from an atom. We did that last night in the lab. The final question in the lab last night was what's the ionization energy for hydrogen, right? Y'all calculated how much energy it would take to remove an electron from the hydrogen atom. It was like 1,310. You're going to see that number again tonight, right? So ionization energy is how much energy does it take to kick an electron out. Electron affinity is the opposite. Electron affinity is how much energy is usually released when you add an electron to an atom. So with ionization energy, we're removing an electron. With electron affinity, we're adding an electron to an atom. But let's not get ahead of ourselves. Let's start by talking about atomic size. There are two ways to look at atomic size. One of them, I think, is common sense, and one of them, excuse me, is not. Okay, let's talk about the easy one. Y'all ready? What happens to the size of atoms as you go down a group or family? Well, the atoms get bigger, man. They absolutely positively get bigger as you go down a group or family. They get bigger. So like hydrogen really tiny, cesium really big, right? I think this is common sense. Okay, where does the size of an atom come from? The size of an atom comes from its electron cloud. The mass of an atom comes from the nucleus, but the size comes from its electron cloud. Okay. Best description I ever heard of an atom is if you blew an atom up to the size of a football stadium, like a professional football stadium. Okay. The nucleus would be the size of a fly on the 50-yard line at midfield. And the electron cloud would be the stadium, would be the seats. The nucleus is so tiny compared to the electron, the area that the electrons occupy. It's insane. Okay. This should not be shocking that as we go down a family, the atoms get bigger because as we go down a family, we're getting a new energy level, right? Hydrogen has electrons in the first energy level. Well, lithium has electrons in the second. So now we're in the second level. Sodium has electrons in the third. Now we're in the third level, right? We're getting bigger as we go out here. So this should not be surprising that the atoms get bigger as you go down a family. It doesn't matter. Pick any family. Pick the noble gases. Pick the halogens, right? Pick the alkaline earth metals. They get bigger as you go down a family. That one, I think, makes perfect sense. This next one doesn't make any sense till somebody explains it to you. So what is the trend? We just did down. What's the trend as you go across from left to right? Well, the atoms actually get smaller. And this is not intuitive until somebody explains it to you. Here's why I don't think it's intuitive. If you find lithium, lithium has 3 total electrons because it's got an atomic number 3. If you find neon, neon's got 10 total electrons. So at first glance, if you look at this, okay, you say, wait a minute, the size of an atom comes from the electron cloud. What you're telling me is something with 3 electrons is bigger than something with 10. And the answer is yeah, that's exactly what I'm telling you. Okay, why is this? What is going on? Well, let's stop and take a look at it. Let's, in fact, write the full electronic configuration of lithium. Let's write the full electronic configuration of neon, and let's draw a picture. picture of both. So here's what I want from y'all. I want the full, not the noble gas. I want the full electronic configuration of lithium, and I want you to draw me a picture. And then I want the full electronic configuration of neon, and I want you to draw me a picture. You know, like with the circles and the dumbbells and the craziness. Yeah, you got this, folks. So hopefully for lithium, you wrote 1s2, 2s1, and we're going to draw our picture. Dot for the nucleus. We're going to change that in a second, but it's got a 1s2, 2s1. Hopefully that's coming back to you from Monday night, right? It's hard to forget it when we just did it, right? Neon, that's going to be a 1s2, 2s2, 2p6. Dot for the nucleus, 1s, 2s, and then you got the 2py, the 2px, and the 2pz. So 1, 2, 3, 4, 5, and 6. Okay. Any questions on that? Now let's try and talk about why this is smaller than that, because at first this makes no sense. Here's why, folks. Lithium has 3 protons in its nucleus. It's atomic number 3. It's got 3 protons. So we got 3 protons, 3 positive things pulling the electrons in here. If we look at neon, neon's got 10 protons, 10 positive things in its nucleus. So this guy has got 10 protons in the nucleus. It's got 10 protons pulling the electrons in. Well, if you think of the nucleus like a magnet, it's easy to see why this guy is so much smaller. Okay, this guy's nucleus is pulling with over 3 times the force, right? 3 times the force of lithium would be 9 protons. This got 10. It is really pulling everything in. Okay, the amount that a nucleus pulls the electrons in is called the nucleus's effective nuclear charge. Effective nuclear charge. That's abbreviated capital Z sub F, Z effective. Okay, Z is the German abbreviation for atomic number or protons. So this is the effective number of protons that the electrons are feeling. So the effective nuclear charge, Z effective, that is how much pull the electrons are feeling. Now, it's a little more complicated than you might think because of a phenomena called shielding, which we're going to talk about here in a second. But here's what's actually happening, okay? Those 10 protons are actually sucking everybody in super tight. So if we wanted to draw this to scale, which I'm not going to make you do, okay? But you do need to know neon is smaller than lithium, right? Because as you go across, in fact, neon is way smaller than lithium because lithium's on this side, neon's on that side, right? And as you go across, they tend to get smaller. If we were going to draw this accurately, neon, you'd have to draw all the orbitals a little tighter. So it's got 10 protons in the nucleus. That 1s, then the 2s, and then the 2p. And neon is smaller than lithium because the protons suck it all in. Now, let's talk about shielding. This electron here does not feel 3 protons worth of pull. And here's why. It's because lower energy electrons are between it and the nucleus. And these lower energy electrons whirl around and block the full pull of the nucleus. We call this shielding. In lithium, the 1s electrons shield that 2s electron from the full pull of 3 protons worth of, for lack of a better word, suckage. Okay? This guy, and you can actually look it up, you can calculate it with some formulas and stuff. We don't need to do that. But this guy's probably only feeling maybe 2.5 protons worth of suckage instead of 3. When you go to neon, neon is not going to be feeling a full 10 protons worth of suckage either, because these 2p valence electrons in neon, they're being shielded by the 1s and the 2s electrons. So they got a little more shielding than the lithium, does, because the lithium only has the 1s shielding, whereas for neon, it's got the 1s and the 2s shielding those 2p electrons. So it's maybe feeling 8 protons worth of suckage, right? Okay. So it is a little more complicated than that. So the true amount of suckage, okay, that these valence electrons in the very outer energy level are feeling is actually called the effective nuclear charge. And you do have to account for this phenomena of shielding. So, just so you're familiar with that, we're actually going to need shielding to describe a couple trends here in a couple minutes. Okay, so that's why we're introducing it now. Shielding is when lower energy electrons block the full pool of the nucleus, okay, by whirling around and creating essentially a negative shield. It's like a force field or a buffer, right, between the nucleus and that outer one. Everybody understand shielding? And does everybody understand how, they don't feel, these outer electrons don't feel the full pool of the nucleus? The only two elements that don't have any shielding are hydrogen and helium. Hydrogen and helium have no shielding. Why do they have no shielding? They have no lower energy electrons, right? Hydrogen is 1s1, helium is 1s2. There's no electrons between them and the nucleus, right? They're in the first energy level. So there's no shielding in hydrogen and helium. Those two elements, that feels a full 1 proton, and helium feels a full 2 protons worth of suckage. No shielding in those atoms. Those are the only two atoms where what I'm trying to say is the atomic number is the effective nuclear charge. For every other element, the effective nuclear charge is less than the atomic number because of shielding. Hopefully, that's a complicated concept. Trying to boil it down, okay? And I don't hear anybody ask too many questions on it, so I'm assuming we're good to go. Which means I just did a phenomenal job explaining it. That's how I like to think of it. So here's what we got. To wrap up what we just spent the last 10 minutes talking about, as you go down a group or family, atoms get larger. Everybody's got that no-brainer, new energy level, getting bigger, right? Okay, but this one is the one you want to put a little star next to, right? And it's a terrible star, okay? As you go across the row, they actually get smaller. And the reason for that is the number of protons increases. That's pulling everybody in tight. All righty, man. If you're a visual person, you can look at this and you can say, all right, yeah, man. Now, it's important to understand that these are trends, folks. There are hiccups. For some reason, fluorine a little smaller than neon. Why? I don't know, and I don't care. These are trends. It's just saying, hey, man, in general, they get smaller as you go this way, right? In general, they're getting smaller. In fact, for that row, I think they do all get smaller. But you can see there's some hiccups, along the way, like, gallium and germanium, same size. It didn't get smaller. As you go down, in general, they get bigger, right? So hopefully, you can see that trend. And by the way, these numbers are in, I believe, angstroms, which are like 10 to the 12th, maybe, of a meter. It is absolutely pouring down rain in here, so hoping that I don't lose electricity. That's always a scare in the summer, with the lightning and the whatnot. Take a second here. Out of these 5 elements, rubidium, strontium, cesium, barium, and chlorine, which would be the largest? Which would be the largest? Rubidium, strontium, cesium, barium, or chlorine? Take a look at the periodic table. Well, hopefully you looked at this, and hopefully you were between these two, right? We should be able to rule out everybody but these two, because chlorine, man, that's up in period 3. Come on, Rubidium and strontium, they in period 5. 1, 2, 3, 4, 5. They're in row 5. But cesium and barium, they're in period 6. Now, who's going to be the biggest? The answer is cesium. Remember, as you go across from left to right, so cesium's chilling here, and then barium chilling right next to it. Good old barium chilling right there. As you go from left to right, they actually get smaller. So cesium is the biggest. If we were going to rank them, cesium's the biggest, then barium, then rubidium, then strontium, and then chlorine is a baby. all the way up there in period 3. Effective nuclear charge, we just talked about that. Shielding, all that jazz. Hopefully you guys are cool with that. Ooh, I love this question. Oh my God, I love this question so much. As in, you're going to find one of these questions on the back test, and you're going to find one of these questions on your next test. Okay, I love these questions. This kills 2 birds with 1 stone. Do you understand Aufbau? Do you understand what it means to be isoelectronic? And then can you apply that to periodic trends? I absolutely positively love this question. I want you to try and think through this. These are isoelectronic elements. Chloride, argon, potassium, the chloride ion, neutral argon, the potassium cation, and the calcium cation. They are all isoelectronic with one another. I want you to tell me, who do you think is the biggest? Yeah, my goodness. Do I love this question? Did I mention that I love this question? All right. So first of all, how are they all isoelectronic? Well, they all have 18 electrons. Hopefully you're able to confirm this. These guys would all be a 1s2, 2s2, 2p6, 3s2, 3p6, right? They all have 18 electrons. They're all isoelectronic with argon. So who's the biggest? The answer, chloride is the biggest. Why? Least number of protons. Let's write down the number of protons, right? The protons determine your suckage, right? How much is it pulling everything in? Chloride has the least amount of protons. If you're looking on a periodic table, which you should be, chloride's rocking 17. Man, I don't feel like writing this. I'm going to type it. Argon's rocking 18. Potassium's rocking 19 protons. And calcium's rocking 20, y'all. What does that mean? Chloride's got the least positive particles sucking in on that electron cloud. Chloride's going to be the biggest. And calcium gonna be the smallest. If you were ranking these in order of increasing size, right? Calcium plus 2 gonna be the smallest. Then it's gonna be potassium, the potassium cation. Then it's gonna be argon. Then it's gonna be the chloride anion is the biggest, right? And if I had sulfide up here, that would be even bigger than chloride because sulfide's only got 16 protons sucking it in. Does everybody understand how you can compare the size of isoelectronic species to one another by looking at the atomic number, therefore the number of protons, and determining who's got the least pull on that electron cloud? Love that question. That is like, you got to understand everything. It's so good. So good. This is good. All right, folks, let's do ionization energy. We talked about ionization energy last night. Okay, you calculated the ionization energy for hydrogen. Actually, turns out that the amount of energy needed to remove a single electron from hydrogen is equal to that Rydberg constant. So that's 2.18 times 10 to the negative 18th joules. And then we turned that into kilojoules and multiplied by Avogadro's number to get the energy to remove a mole of electrons, which is called an Einstein, right? This is the generic equation for ionization energy. Take some element in the gas phase, and how much energy do I need to zap in here to turn it into the +1 cation and kick that electron out of the atom, right? What are we doing? We're taking an electron from this neutral element and we're kicking it out of the atom, and you're left with the potassium cation, or whatever, the element X cation. Okay, could be potassium, could be sodium, could be chlorine, could be iron, could be whatever, right? Because this is our generic expression. In general, the smaller the atom, the harder it's going to be to remove that electron. Because the closer that electron is to the nucleus, the harder it's going to be to pluck it out of there, right? The more energy you're going to have to put in to remove it, to pull it away from the protons. So small atoms tend to have high ionization energies. And big atoms tend to have very small ionization energies because those valence electrons are not very close to the nucleus. You can just, it's like the nucleus doesn't even know it was there. So big atoms have very small ionization energies. They take very small amounts of energy to remove electrons. And small atoms have high ionization energies. It takes a lot of energy to kick electrons out of there. So you have to know the trend for size to know the trend for ionization energy, right? If we know the trend for size, as you go down, they get bigger, right? So what does that mean? That means ionization energy would decrease as you go down because it's easy to take electrons away from these big atoms. As you go across, they get smaller. So that means as you go across, okay, the ionization energy increases because they're tiny, it's going to be harder to take electrons away from. Helium has the highest ionization energy of any element in nature, and francium has the lowest ionization energy of any element in nature, right? You can think of it like this. If you go diagonally from helium to francium, the ionization energy is decreasing here, right? Or if you go diagonally from francium to helium, it's increasing as you go that way, right? You know me. I love a good graph. My goodness, do I love this graph. I love this graph so much. Oh, hey, by the way, what was hydrogen last night? 1,310. There it is, right? You calculated that last night. You guys are doing quantum physics. Come on. That's exciting. Anyway, I love this graph. This is a beautiful line plot of the first 86 elements on the periodic table. And this line plot shows us a couple things. This is so beautiful. Number one, here are the periods, right? So here's period 1. That's right there. Here's period 2. Period 2 is right there. There's period 3 and period 4, row 4. And then here is row 5. And then here is row 6. Here are our rows. What is the first thing you should see? As you go across the rows in general, the ionization energy, I'm going to switch colors here. As you go across the rows in general, the ionization energy is increasing, right? In general, we have an increase in ionization energy as we go across the row. Okay, that's the first thing we should see. Next thing hopefully you see is that it's not a law. There are some blips. We go on, I don't like green. I mean, I actually like green. Green's my favorite color, but I don't like the way the green is showing up here. How about orange? That's better. Okay. You should notice it is not a straight line. We got some hiccups, and the hiccups seem to be coming at like the same spot. We'll talk about that in a second. We're going to explain those hiccups. The next thing I want you to see, though, is let's look at these. I'm going to borrow a term from calculus, these relative maxima. Look at the highest points on the graph, and then let's look at the lowest points on the graph. What do we notice about the relative maxima and the relative minima on this graph? Well, hopefully what you're noticing is that the relative maxima are the alkali metals. These are the alkali metals. And hopefully what you notice in, oh, I'm so sorry. I was looking down here and I'm typing at the top. Oh my gosh. Hopefully what you're noticing is that the relative maxima are the noble gases. And hopefully what you're noticing down here is that the relative minima are the alkali metals. What is this trying to show? Well, in every row, the hardest element of every row to take an electron away from are going to be the noble gases. And the easiest element to take an electron away from in every row are the alkali metals. So those the alkali metals are local minima, and the noble gases are our local or relative maxima in every spot on this graph. So love that line graph. It's beautiful. Can tell you so much. If you're into like straight up numbers, I got a graph somewhere. I thought I did. Yeah, go back. Come on now. Here's the numbers in like a bar graph. It's like a crazy thing. But again, you can see in general as we go across from left to right, ionization energy is increasing. Ionization energy is increasing. Ionization energy is increasing. Oh, by the way, there's that. What did we get? We got 1,310 last night. There's that number again. You calculated that last night. That's so cool. Okay, we're going to explain those hiccups here in a moment. But first, I want to talk about, well, you know what? Let's do the hiccups. Let's do them now. Why do we see a drop in ionization energy? Uh-oh. I'm hoping I didn't lose you guys. I just had lost power there for half a second. I'm hoping we still good. Can you guys still hear me? I'm gonna stop my share. Can you still hear me? All right, good. The lights flickered. You probably saw it. It was crazy. All right, good. I'm telling you, man, my biggest worry is in the summer. Losing power. Never good. Okay. So what do we got going on here? Why do we see a drop here from beryllium to boron and from nitrogen to oxygen? Why do we see a drop in ionization energy from magnesium to aluminum and a slight drop from phosphorus to sulfur? Why do we see a drop from calcium to gallium and from arsenic to selenium. What is going on here? Okay, well, I call this the S to P drop, and I call this the P3 to P4 drop. So I call this drop the S to P drop, and I call this drop the P3 to P4 drop. And I want to explain these drops to you. So let's start with beryllium and boron and get right to it. So here's what we need to do. So beryllium and boron. Here's what I want you to do, guys. I want you to write the full electronic configuration of beryllium, and I want you to draw me a picture, like actually draw it. And then I want you to write the full electronic configuration of boron, and I want you to draw me a picture. We're going to need to look at it to see why you would have a drop in ionization energy. You got this. Full electronic configurations, draw me a picture. Beryllium. Beryllium is a 1s2, 2s2. And boron is a 1s2, 2s2, 2p1. Let's draw. Beryllium, dot for the nucleus, got a 1s and a 2s. Boron, dot for the nucleus, got a 1s, a 2s, and then it's got a 2p set of orbitals with one electron chilling up there. Why is it actually easier to steal an electron from this boron than it is from beryllium, even though boron is smaller? And technically, again, boron is smaller. I really should have drawn it smaller. Why is boron smaller? Boron's got more protons. Boron's got 5 protons. Beryllium's got 4 protons. What's going on here? Why is it actually easier to steal this electron even though it's smaller? Here's why. It's got way more shielding. If we look at beryllium, beryllium's valence electrons are only being shielded by this 1s orbital. But if we look at boron, it's got like double the shield. Boron's valence electron, that its highest energy valence electron, that 2p electron, is being shielded by a 1s and the 2s. So think about that. It's like it's easier to pluck that electron out of there because it's being blocked by the full suckage of the nucleus, and that's why it's easier to take that out. When you go from the S to P, when you do that S to P jump, when you go from beryllium to boron, magnesium to aluminum, calcium to gallium, right? When you do that S to P jump, there is a decrease in ionization energy because the s orbital is now shielding that p orbital. Okay, yeah. So like if I was going to write down like a summary of it, I would write, the the P1 element has additional shielding from the previous s orbital. Yeah. How we feel about that? So that's the S to P thing. Now I want to talk about the P3 to P4. So I would like you to write and draw. I know. Y'all thought you were done with alpha. There's a reason we do alpha before periodic trends. That's because you got to use alpha to explain a lot of these periodic trends, or at least the hiccups in the trends. I would like you to write the full electronic configuration of nitrogen. Draw me a picture. And I would like you to write the full electronic configuration of oxygen. Draw me a picture. You got this. Nitrogen. Nitrogen is a 1s2, 2s2, 2p3. You can do this if it helps. If we're going to draw it, dot for the nucleus, you got your 1s, you got your 2s, you got your 2p3. Love it. Going to come back to that in a second. Oxygen, 1s2, 2s2, 2p4. One, two, three, four. All right, what is going on here? Even though oxygen is smaller than nitrogen, why is it easier to pluck an electron out of there? This is pretty cool. You ready for this? Here's why. Okay, when you remove an electron from oxygen, you eliminate electron-electron pair repulsion. Okay, let's zoom in on this py orbital. We look at this py orbital where I'm showing both electrons. What's going on here? Well, if you look at nitrogen, there's no doubling up in the p subshell, but oxygen has doubled up. Okay, it's actually doubled up each one of these a third of the time. We're going to talk about that in a second. Okay, but what's going on here? Okay, we now have two negative particles, two negative electrons being forced to occupy the same space. Well, do they like doing that? Opposite charges attract, like charges repel. So by forcing two negative particles into the same area, you increase the energy of the atom. Okay. Now there's nothing oxygen can do about it. It's at 4. It's going to singly occupy. Then it's going to go back and double up. But that's why it's actually easier to pluck an electron out of oxygen. Because when you pluck an electron out of that p subshell, you now eliminate electron-electron pair repulsion in the entire p subshell. When we have neutral oxygen, that electron actually spends a third of its time here. It spends a third of its time here in this one, and then it spends a third of its time here in this one. So each one of those orbitals has like a third of an electron-electron pair repulsion. But we can't obviously write that. There's no way to write that. But when we remove that electron, we eliminate electron-electron pair repulsion in the entire p subshell. Okay, if you go up to nitrogen, removing an electron from nitrogen, there was no electron-electron pair repulsion there to begin with, so we're not eliminating any electron-electron pair repulsion. So oxygen actually says, hey, you know what? Go ahead and take this electron. It's creating all kinds of hassle for me, right? Okay, like it's fighting with the other electrons. Go ahead and take it. And that's why it's a little easier to take an electron from oxygen. It's why oxygen has a lower ionization energy. So for what I call the P3 to P4 jump, removing an electron from a P4 element is easier than a P3 element because it eliminates electron to electron pair repulsion. Pretty cool. So let's go back and look at these trends. We can now explain what's going on here. We said that, when you go from the S to the P, you get a drop because these guys are now shielding the P electrons. And when you go from a P3 to a P4, you get a drop because when you move an electron from a P4, you eliminate electron-electron pair repulsion for the entire P subshell. So yeah, that's what's going on there. That's good stuff. Good stuff. All right, let's go back. Go ahead here. Which of these elements has the largest first ionization energy? Be careful. B Careful. Who's got the largest first ionization energy? Go ahead. Hopefully you picked, drum roll please. Hopefully you picked nitrogen. Talk about why. This is row 2. So if we're looking at a periodic table, beryllium over here, oxygen over here, right? But why nitrogen? Well, you got to remember oxygen is a P4, so you get a drop, right? If we go to the next slide, what's going on, right? So we're here in row 2, period 2. When we go from nitrogen to oxygen, it actually drops. Nitrogen is the highest out of those 5 elements that were listed because oxygen is a little lower than nitrogen because it eliminates electron-electron pair repulsion. All right. Love that. That's good stuff. So we just did that. That's good. Okay. I want to talk about successive ionizations. So I'm going to jump back. Pardon me here for jumping around a little bit, trying new stuff. I think that went well. Different order. All right. Why stop with just one electron? Why not take more electrons? Well, you can totally do that. You can do what are called successive ionizations. However, it is going to always take more electrons, or I'm sorry, it's always going to take more energy as you remove more and more electrons. So the second electron is going to be harder to take than the first, and the third electron is going to be harder to take. It's going to take more energy than the second, and the fourth electron. So as you take more and more electrons, you need to ante up more and more energy. And there will eventually be a gigantic jump in ionization energy. Let's talk about this. Okay, I want to write the noble gas configuration of aluminum. So aluminum, oh my gosh, I hate typing this out. But aluminum is going to be a neon in brackets. So we got brackets, we got neon in brackets. You know what? Nope, not doing it. I'm writing it on the board. Just looks too terrible. Alrighty. Regular old neutral aluminum gonna be a neon in brackets. Then gonna be a 3s2 3p1. Cool. I want to talk about what happens when we remove electrons from aluminum. So if I want to remove the first electron from aluminum, so if I start with neutral aluminum and I zap in some energy and I take an electron away, I'll be left with the aluminum plus 1 cation and an electron. Now that's going to take some energy. How much energy is it going to take to do that? Well, it's going to take, I have it on this slide, 580 kilojoules per mole. This is called ionization energy 1, IE1. And it's the amount of energy needed to remove the first electron. So that's 580 kilojoules per mole. So what did we just do here? Well, if I take aluminum and I turn it into aluminum plus 1, I just removed that guy. Cool. But what if I get greedy? What if I want to take this aluminum plus 1 cation, and what if I want to take another electron away? And I want to turn this into aluminum 2 plus and an electron. What if I want to go take that guy and make it 2 plus? Well, now you want to pay more energy. Okay, this already had a positive charge. Static charge is unstable. Making it now have a positive 2 charge is even more unfavorable. The amount of energy needed to remove that second electron, that's called ionization energy 2. The amount of energy needed to remove the second electron in aluminum, that's going to cost you 1,815. So we have more than triple. Okay. What if I want to take another one? Man, I'm getting super greedy. Things are getting crazy. I want to remove a third electron from aluminum. I want to and take that to aluminum 3 plus. Well, it's going to take even more energy. Ionization energy 3. is 2,740. That's 2,740 kilojoules per mole. Now, what if I want to remove another electron? Well, now we got problems. You are now going to see a massive jump. If you try to take a fourth electron from aluminum, the ionization energy to remove that fourth electron, okay, because now I would be getting into the core electron. Every electron I took so far was a valence electron. But now this fourth electron that I would try to take would be a core electron. I now need to dip in to the 1s2, 2s2, 2p6. I need to dip into its core electrons, and I got to try to take that guy away and make it a p5. Removal of a core electron, because it's one energy level closer to the nucleus, you can imagine way higher. How much higher? Oh my goodness. It goes up to 11,600 kilojoules per mole of energy. You will get a massive jump in ionization energy when you will remove a core electron. Put another way is this. There will be a large jump in ionization energy when you have gone one more than the number of valence electrons. So aluminum has 3 valence electrons. The fourth ionization will be massive, massive. I absolutely, positively love this table right here. This table is from my high school chemistry textbook. I know. Crazy. Zoomdall, the Zoomdall textbook from like 2004 or something. Okay. I love this table so much that when I started teaching chemistry, I went back, found a copy of the book, scanned it, and popped it in here. Of course, I have full copyright. I mean, there's no reason to check up on that or anything. Okay, but I love this table. This is the only table that I've ever seen. It's the only table I've seen set up this way. And what it is designed to show is that large jump between ionization energy, or the large jump in ionization energy between the removal of the last valence and the removal of the first core. If you look, right, look at sodium. Sodium's only got one valence electron. So the second ionization, we get a big jump. Magnesium's got 2 valence electrons, third ionization, big jump, right? Aluminum, we just looked at that one, 3 valence electron, fourth one, big jump. And they put a staircase here to show the difference in energy between the last valence and the first core. Man, I love that, right? Okay, if you look at my back test, and if you look at the test, the next test you're going to take, I haven't even written it yet, but when I do, there's going to be a question about this. Absolutely, positively, right? Okay, like if I give you a set of data, like, I don't know, say I gave you this set of sulfur data, and if I said, hey, which ionization took or if I give you this set of sulfur data, which ionization took the first core electron, it's this one, because you get a huge jump, right? Here, they're just kind of going up, right? But here we get this huge jump. You should also, if I give you a set of data, right, if I give you something like that, and then if I said, hey, what third row element could this be, or would this most likely be, right? We are in the third row, we are. You should be able to look at this and say, oh man, this element's got 4 valence electrons because the fifth took a core. What third row element has 4 valence electrons? Oh, that's silicon. Okay, so love asking questions about that. Absolutely love it. All right, we already did that. We did that. Oh, here we go. This is what I was talking about. This is what I was talking about. Which element from period 3 is this most likely to be? Take a look at that data. Take a look at a periodic table. See if you can't tell me what third row element that is most likely to be. All right, hopefully you looked at this data, folks, and you said, oh boy, big jump between 5 and 6. There must be 5 valence electrons. Which of these elements has got 5 valence electrons in the third row? Phosphorus. This would be phosphorus. This is, this is core, this is core. They're both high. Okay, that big jump happened there. that tells you there were 5 valence electrons. Phosphorus is the element with 5 valence electrons. All right. Electron affinity. We'll do electron affinity, then we'll take a break. Electron affinity, ladies and gentlemen, tells you how much energy in general is released, okay, when you add an electron to an atom. Now, this is almost always exothermic event. This almost always releases energy. So we're gonna write that down. Almost always releases energy. Why is that? The electron is going to be more stable inside the atom than it is floating around in space. A negative electron floating around, not being stabilized by a nucleus, highly unstable. So we're taking one of these unstable electrons, we're now adding it to an atom. That almost always makes it more stable. Okay, there are 3 exceptions. They are the exceptions. They are the noble gases, nitrogen, and phosphorus. Those, I want to say 3 things, but it's really like what? It's really like 8 things, right? Because there's 6 noble gases, not counting 118, which is ridiculous. But those 8 things: helium, neon, argon, krypton, xenon, radon, nitrogen, and phosphorus. Those elements are the only ones that actually it requires energy to add this free electron. They would have positive electron affinities. Why is that? Well, I'm glad you asked. Oh, nope. Let's go back. So, first of all, the noble gases. Let's start there. The noble gases, they do not want another electron. If I add an electron to neon, I now have to go up to the 3rd energy level. It's not happy about that, right? Because now I'm starting a whole new energy level. That nucleus doesn't want to try to hold electrons in a whole other energy level. So that's why it actually takes energy to put an electron into a noble gas. They also have a full octet, right? They found the meaning of life. They have 8 valence electrons. They don't want any more. They're happy. Now I'm throwing that whole, feng shui off by putting an extra electron in there. Not happy about it. What's up with nitrogen and phosphorus? You're going to love this. If I write the electronic configuration, nitrogen, phosphorus, and you can do noble gas, it doesn't matter. Nitrogen is going to be a helium in brackets. 3, nope. How about a 2s2, 2p3. Phosphorus is going to be an argon in brackets. 3s2, 3p3. Take a look. If I add an electron to nitrogen, make nitride, it's now a P4. If I add an electron to phosphorus, it's now a P4. What just happened? This is the opposite. It's really the same thing as that P3 to P4 hiccup or jump that we were talking about before. When you add an electron to nitrogen or phosphorus, you are creating the electron-electron pair repulsion throughout the entire subshell. It's easier to take an electron away from oxygen or sulfur because they're P4s and you eliminate electron-electron pair repulsion. For that same reason, nitrogen and phosphorus don't want an electron because it creates electron-electron pair repulsion throughout the whole subshell. So that's kind of an important idea, is this electron-electron pair repulsion, okay, thing that comes up with P4s, okay? With oxygen and sulfur, you're getting rid of a P4, and with nitrogen, that's for ionization energy. And for nitrogen and phosphorus with electron affinity, you're creating a P4. P4s are less stable than P3s because of electron-electron pair repulsion. Cool. Man, that is periodic trends. This is